So, in the last lecture we saw how a basic pipeline works and how it helps in getting a significant degree of speed up over an equivalent non-pipeline implementation of a certain piece of hardware. Now, in this lecture we shall give some illustrative example where you will be able to see, given some computation that we want to implement in hardware, how we can implement it in the form of a pipeline and how we can code the corresponding module in Verilog. Okay. So, the title of the lecture is pipeline modeling. So, here we shall be considering a very simple pipeline structure comprising of 3 stages. The pipeline computes some hypothetical computation which is defined as follows. Let us suppose there are 4 numbers a, b, c and d which are given as input to the computation, and finally, we want to get f as output. So, what we are saying is that we have a piece of computation. If you treat it as a black box, there are 4 inputs a, b, c and d, and there is one output, the final output, that is f. Let us see what is there inside this computation box. So, all these a, b, c and d are multi-bit vectors. Let us in general call it n. So, we can define a parameter to fix some value of n later. Similarly, f is also an n bit vector which is as output. Now, the computation that is done is as follows. First, a and b are added, the result is stored in another temporary variable x 1, c minus d, d is subtracted from c, we store the result in x 2, then this x 1 and x 2 are added to another variable x 3, finally x 3 and d are multiplied to get the final result. Now, in order to have this in a pipeline, we observe the dependencies. See, there is an obvious dependency. The first line, there are 2 statements which are computing x 1 and x 2, which are used in the next statement. So, the next statement cannot be executed at the same time as we are executing the first 2. So, this has to be in the next step. Similarly, after x 3 is computed, only then we can compute f. So, quite naturally, we have divided this overall computation into 3 stages, we call them S 1, S 2 and S 3, right. Now, let us look at one thing. See, 3 stages S 1, S 2, S 3 we have divided our computation into. So, let us represent that like this. This is our stage S 1, let us say this is our stage S 2 and this is our stage S 3. You see, there are a few things you need to observe. We shall be showing this using some diagrams later. In the first stage, A, B, C and D are the inputs that are coming from outside. So, when you are starting computation in the first stage, you must have the 4 inputs which are coming in A, B, C and D. Then you see, the first stage is computing the temporary values x 1, x 2 which will be forwarded all right to the next stage. So, next stage is computing x 3. So, from here there will be some computation, this x 1 and x 2 will be forwarded, x 1 and x 2 will be forwarded to the next stage. Look at the third stage is taking x 3. So, what is x 3? X 3 is computed in stage 2, it takes x 1 and x 2 as input, it computes another value x 3. Now, in S 3, whenever you are doing the calculation, you are not only taking S 3, you see, you are also taking the value of D. Okay. So, this value D which was here, this also has to be forwarded up to this place, so that S 3 can be computed and finally, you can get the value f generated. So, these intermediate buffers or the latches will be used to store this value. For example, D has to be forwarded. So, you will also have to store D here, you will also have to store D here, and then finally, F will be calculating the value. Because you just remember one thing. So, when we are giving the first set of data, let us call them D1. So, D1 will first be executing on stage S1, then D1 will be moving to S2. When it is moving to S2, so S1 will be starting with the next data D2. Sorry, this is D1. Similarly, D1 will be moving finally to S3, then D2 will be moving to stage 2 and the next data will be entering stage 1. Now, the point to notice that when the computation for D1 is entering stage 3, so the value of A, B, C, D which were provided for D1, that should be available here. That is why we have forwarded that D value up to this place. So, this same value will get forwarded because when D1 is doing this computation, this is the D of D1. In the meantime, S2 is calculating for D2. So, whatever D is stored here, this is the D value for D2, and whatever D is coming, that is the D for D3. Okay? So, this is how it goes on. So, here we have an example to illustrate diagrammatically. So, this is the computation that we want to do. Okay? Fine. So, this is the pipeline diagram that we are just assuming. You see, in the first stage, as I said, we are doing two calculations, A plus B goes to x1, C minus D goes to x2. You see, in the first stage, the values that are coming are A, B, C and D. So, A plus B goes to x1, C minus D goes to x2. So, we are assuming that the delay of both addition and subtraction are 4 units. So, delta is the delay of this block. And because D will be needed later, as I had said, so the value of D is also forwarded here. In stage S2, we are doing x3 equal to x1 plus x2. So, there is another adder which takes x1 and x2 and it generates x3. In the last stage, there is a multiplier. So, we assume that the delay is 6 units, it multiplies x3 and D and generates F as the result. Now, in this pipeline, what we are saying is that in order that you can execute these operations in a pipeline, because you see what is the essential advantage of a pipeline? When there are a number of data sets on which we want to perform the same kind of computation. Let us say for this example, let us assume A, B, C, D are vectors in the sense that it is like an array. There are, let us say, 1000 sets of data which are coming one by one, A, B, C, D, first value, second value, third value, like that. So, as these values are coming like this, computation in a pipeline becomes very efficient. Okay? Now, in order to do it in a pipeline, you will have to insert, as I said, latches or registers in between the stages, because when the first calculation is over in stage 1 and now you move to stage 2, these temporary results x1, x2 and also this D, they must be held somewhere so that stage 2 can start. Why they must be held somewhere? Because the next set of ABCD values are already here. So, those values will make the x1, x2 and D values to change. So, while S2 is computing, in order to ensure that these values do not change, we must have a storage element in between. Similarly, between every stages you need storage elements like this. Okay? So, these storage elements we refer to as this L12, L23 and L34, and just for convenience these variables, you see earlier we called them x1, x2 and D, like. So, here we are renaming the variables by also mentioning which latch stage. This is L12 between 1 and 2. So, L12 underscore x1, L12 underscore x2 D. Similarly, L23 underscore x3, D. You see D is being forwarded. So, the value of D when it reaches here we call it L12 underscore D, and when that value reaches here we call it L23 underscore D, and finally, when we store the value f here we call it L34 f, because there will be a fourth stage I am assuming after this, right. Okay. Now, you see let us consider this L12. So, in L12 we need to store 3 values. So, it is not that x1, x2 and D are 3 registers that you need to have separately from the latch stage. Rather, this latch is nothing but they will be allocated storage here itself for the variables. x1, x2, D they will be allocated storage here itself, x3 and D they will be allocated storage here, and f will be storage allocated here. Like it is something like this. These are the individual register elements, let us say, or the latches. This latch stores L1 to x1, this stores L1 to x2 and so on. Now, these 3 latches taken together we call them as L12. These 2 taken together we call it L23 and this is L34, right. So, this is our pipeline diagram which you want to code in Verilog. Now, when you code in Verilog we need to remember the name of these variables L1 to x1, L1 to x2, L1 to D, because these are the variables we have to generate, because all these latches are storage elements that need to be assigned values in synchronism with some clock. Now, just one thing we are assuming here for the time being, that here there are some latches, right. I am showing the latches like this. There are 3 stages. There is a stage S1 here, there is a stage S2 here, there is a stage S3 here. So, what we are assuming is that there is some kind of a clock which is connected to all the latch stages like this. Data moves through the pipeline stages in synchronism with the clock. Now, we shall see later that what kind of clocking mechanisms are better for these register stages, we shall see it later. For the timing, let us assume that there is a common clock which is feeding all the register stages like this, right. Okay. Let us see. Now, we want to code this in Verilog. Let us see how we do it. So, we define a module, the name of the module is pipe underscore ex, and these are the parameters. F is the output, A, B, C, D are the 4 inputs, and of course, a clock is there. And parameter we are defining as 10, so that all the numbers are 10-bit values. So, A, B, C, D are declared as input 0 up to n minus 1, clock is also an input, this F is an output of n bit again. Now, this output F I have not declared as reg because I am just assigning a value using the assign statement, but all the temporary values like this L1 to x1, L1 to x2, L1 to D, L23 x3, L23 D and L34 F. Look at the previous diagram, all these values 1, 2, 3, 4, 5 and 6, they are all declared of type register because you will be storing them in the latches. They are all declared of type reg again of size n. And the last value this L34 F, that is nothing but F, right. So, we are simply assigning it to F. Now, regarding coding, as I said, all computation will be done in a synchronous way, always at pos h clock. So, what will happen when a positive edge of clock comes? For stage S1, whenever a clock comes, A and B has arrived, after a delay of 4, this L1 to x1 will get the value of the sum, we will have to store it here. Again after value of 4, C minus D will be stored here, L1 to x2, and D will be stored directly here, we are assuming there is no delay. Okay. So, in terms of the declaration, we are using non-blocking assignment, we are writing L1 to x1 assign with a delay of 4 A plus B, x2 c minus d, and this gets d. And these three statements constitute our stage 1 of the pipeline. Okay. Then comes the stage 2. So, in stage 2 what we are doing, just go back once. In stage 2 we are taking the values of L1 to x1 and L1 to x2 and we are storing the sum into L23 x3, and d we are moving straight. So, there are two things, this L1 to x1 and L1 to x2 are added, after a delay of 4 it is assigned to L23 x3, and the value of d is simply copied from L12 to L23. And in stage L3 you are doing similarly a multiplication with a delay of 6, and the result, and multiplication you are doing on L23 x3 and this L23 d, and the result you are storing in L23 L3 for f. So, this is as simple as that. You have the pipeline diagram and we have simply coded the pipeline specification in the form of the different stages inside an always block, which are triggered with a clock. So, translating a pipeline schematic diagram into a Verilog code is fairly simple, as we have seen. Once you have the diagram, you can directly start writing the Verilog code from there. Okay? Fine. Now, there is another alternate style that we are showing here. So, you can do the same coding in a slightly different way. You see here what we did, we used a single always block, right, and inside the always block the first three statements were stage 1. Of course, we wrote a comment here just to indicate that these three are stage 1, these two are stage 2 and this is stage 3. But suppose if I do not write the comments, then it would be a little confusing to the reader, the person who sees the code, to identify that which one is my stage 1, which one is my stage 2 and which one is stage 3. So, in the alternate style what we do, we split or break the always block into 3 smaller always blocks, one for stage 1, one for stage 2 and one for stage 3, okay, like this. The first part is identical. Now, this is the always block for stage 1. You see there is a separate always block, begin and end, the 3 statements for stage 1 are coming here. Then there is another always block for stage 2 and another always block for stage 3, because there is a single statement, you do not need begin end. Now, this style is equivalent to the previous one, but this code is more readable, because you are showing the stages separately and the persons who is seeing it will be very easily able to appreciate and understand the stages. Okay? And there is another reason that we will see later with another example we shall discuss, that there is another need why we need to break it up into multiple stages. Now, let us try to write a test bench for this. Now, in this test bench what do we need? We need to supply 4 values a, b, c and d, and after some time we will be getting the result f available with us. So, here we are instantiating this module, these are the parameters. Now, this a, b, c, d are the inputs to the pipe. So, these will be declared as reg, because here we will be assigning values, clock is also reg and f is the output which is declared as wire. So, in a similar way these are all 10-bit values, and we are applying a clock. You see the way we are applying clock is 0 and with a delay of 10 we are complementing it. So, the clock will be like this. If this is 0, this will be 10, this will be 20, this will be 30. So, after 10 intervals the clock is toggling, changing state, right. This will be our clock, right. Next what we do, we apply the inputs. Now, let us see what we do. The first set of inputs, there is another initial block. So, it starts with time 0 again. We give a delay of 5 and apply the first set of inputs. What does this mean? So, you see here is a timing diagram, clock starts with 0. So, time 5 is somewhere here, right, this is 5. So, it is here we are applying the first input. Why? Because when the next clock edge comes, this input is already ready. So, we can start processing this input from the next clock edge. And after this we are giving 20-20 gaps, because this was 5, next it will be 25, it is here. Next it will be 45, it is here. So, my first input is coming here, second input will come here, third input will come here, and so on. The reason is very clear, that if I apply the first input here, then the first clock edge will be able to capture this input. If I apply the second input here, the second clock edge will be able to capture it. Similarly, the third clock edge will be able to capture it. So, in this way we are applying the inputs. So, there are a set of 8 sample inputs we have applied, various values of ABCD. So, initial delay of 5 and then 20-20-20 gaps. So, here also by the side I have shown the expected value of the result. For this thing you see A plus B is 22, C minus D is 3. So, 22 and 3, what you are doing? You see that computation once more, you are doing the addition, then subtraction, then you are adding this x1 and x2, then you are multiplying it with D. Okay. So, 22 and 3 you add them up, it becomes 25, 25 you multiply with D, it becomes 75, like that. Okay. These are the values in decimal, and side by side I am also showing the hexadecimal values, because in the timing diagram that will be generated by GTK wave, the values will be shown in hexadecimal. Okay. Now, in this initial block we are specifying the dump files and dump variables, and we will be monitoring the time and the values of f. So, time and f will be printed. So, we will be doing simulation up to certain maximum time, let us say 300, but here we do not need 300, because we have only how many 3, 4, 5, 6, 7, 140, by 150 it should be over, but anyway we are doing up to 300. Now, if you run this simulation, the simulation result comes like this. Okay, the time is whenever f changes, okay, time is whenever f changes, and you see the f values are 75, 66, 112, the same values are coming. Okay. So, whatever are the expected values, the same values are being generated. Okay. This is the final output, and if you see the output of the GTK wave, the timing diagram, here you can see what is happening. You see the first row shows the clock, this A, B, C and D are being applied, you see 0, 0, A, C, 6 and 3, that means 10, 12, 6 and 3, and the values of x1 and x2 are getting calculated. 10 plus 12 is 22, it is 16 in hexadecimal, it is 22. 6 minus 3 is 3, this is 3. These two are again added, 22 and 3 is 25, it is 19 in hexadecimal, this is L23x3, and this is multiplied by D. Okay. Finally, you get here 48, that means 16 4 is 64 and B 75, 11. So, this is your final result, and this is assigned to final f. So, you see 4B 42703, these are the actual values, 4B 42703 I have shown in hexadecimal, the same values are coming in the simulation output, and it is coming at every clock as is expected in a pipeline. So, the advantage of the pipeline is that you are not waiting for one computation to finish before applying the next input. So, you are continuously applying input one after the other every clock, and when the pipeline is full, output will also be generated once per clock cycle. That is why the throughput will be improved to a great extent. Okay. This is illustrated by this example, this diagram. This timing diagram as is shown, you can see from here that the output is also generated once per cycle, see first output, second output, third, fourth, fifth, sixth, but initially there is a delay for the pipe to fill up. but once the pipe gets filled up, the outputs are generated 1 per cycle. Okay? That is the advantage of pipeline. Now, there is an important point to note that in the example that I have shown here, we have used a single clock, and that clock is used to activate all the latches. So, we have used a single statement always at the rate passage of clock. So, it is actually a flip flop, a register we are implementing. Okay? At the positive edge of the clock, we are just activating the latch stage. That same thing is happening for all the stages, right. Now, the point to notice that this is actually a warning that in a real pipeline, this may lead to a race condition. See, what we are saying is that in order that correct operation is achieved in a pipeline, all the register stages or latch stages, if you are supplying a common clock, must be master slave type. There must be a master stage, a slave stage, and so that inputs and outputs are perfectly isolated. But if you do not use master slave flip flops or latches, a single stage, then when the input changes, the output also changes, which might affect the second stage. That is the danger here. Of course, in this example you could not see that, but in the next example we shall see in our next lecture, there we will do this isolation in a very proper way. So, what are the possible solutions? As I said, first one is to use a master slave flip flop, and the second one is to use a two-phase clock to clock the alternate stages. So, we shall be illustrating this in the next example, which we will be taking up in our next lecture. So, in this lecture we have taken a simple example of a computation and showed how we can map it to a pipeline structure and how we can code it in Verilog. Thank you.